Hello and welcome. I hope you're doing well. I recently saw an article discussing a new carbon conversion technology being developed here in Australia by RMIT University. It prompted me to investigate how many other systems are being developed along similar lines around the world. This technology is showing promise across many projects, so let's take a look at several of them and see what's happening. I'll give a brief summary of each project and talk about what stage they're at. I've derived the summaries from several articles on each project. All of them are listed in the description. Let's start with the Royal Melbourne Institute's conversion device here in Australia. This system combines the removal and conversion into a single stage. It is designed for carbon capture and conversion at the emissions source, and it produces ingredients that can be upgraded to low emissions jet fuel and other products using proven industrial processes. It does not require highly purified CO2, which is an important property when capturing industrial emissions. The device is based on tandem amine scrubbing and CO2 electrolysis. They are achieving a 60 to 92% conversion rate. They have completed a 3 kilowatt test system and are looking to develop a 100 kilowatt demonstration system within 5 years. Next, we have a project developed by MIT and Harvard in the US. Their system is designed to produce formate as the output. Formates are salts containing the formate ion paired with a metal. Their energy density or storage capacity is inferior to hydrocarbon fuels. However, it's very stable, particularly when reduced to its powdered form, and can be stored for decades in ordinary steel tanks. Formate can be used within fuel cells to generate electricity, which would be best suited for residential installations with the unit minus the storage tanks about the size of a fridge. The system uses an alkaline solution to capture the CO2, and then a cation exchange membrane electrolyzer is used for the electrochemical conversion. It is important to note that this system is designed to capture CO2 from industrial output or open air. This technology is achieving high conversion rates of 95 to 96%. The system is not in commercial use and is still in the development stage. NASA has developed a solar-powered conversion device. It uses metal oxide thin film devices that are designed to capture and convert CO2 at the emissions source. This nanomaterial is designed to be low cost to manufacture and primarily uses the UV and IR ranges of sunlight for power, with titanium dioxide composites performing the conversion. This technology is available for licensing by NASA, but its weakness is that it only achieves a 5 to 8% conversion efficiency, with other technologies achieving rates over 90%. Turning to the National Taiwan University, where they are developing two technologies, a membrane carbon capture and an electrochemical carbon conversion. The capture membrane uses an innovative ultramicroporous metal organic frameworks, or MOFs system. These MOFs are blended with polymers to create membranes that can selectively remove CO2. The electrochemical conversion is highly efficient and converts CO2 into syngas, formic acid, ethanol, or ethylene. It has low energy consumption and can be powered from solar arrays. They have a prototype system currently processing 50 kilograms per day of CO2. A research team from the Korea Research Institute of Chemical Technology have developed a cascade conversion process based on zeolite catalysts to produce gasoline and naphtha. The system circulates CO2 and hydrogen and produces the hydrocarbon conversion in a single stage. Any unreacted gases are recirculated in this system, meaning a CO2 conversion rate of over 90%. They have partnered with GS Engineering and Construction and Hanwha Total Energies to build a pilot plant producing 50 kilograms per day. Using data gained from the pilot project, they are seeking to build commercial-scale plants producing 100,000 tonnes annually. Finally, Cambridge University have developed a dual-bed flow reactor that converts CO2 from the air into syngas. They base their approach on photosynthesis found in plants. The system absorbs CO2 from the atmosphere at night and then uses solar power during the day to do the conversion. The carbon capture bed uses solid silica amine absorbent material to capture CO2 during the night. During the day, concentrated light is used within the reactor bed to release the CO2. It is converted to syngas using silica alumina titania cobalt to pyridine molecular semiconductor photocatalyst. That's a mouthful. This technology is still in development stage with several key engineering obstacles to overcome. There are currently up to 50 large-scale carbon capture plants around the world, capturing about 50 million tonnes of CO2 annually. The most common technology used at present uses liquid amine to bond with the CO2. The CO2-rich liquid is then subject to heat to break the bond, and the CO2 is compressed for storage. The cooled amine solution is recycled back to the capture phase. They are not energy efficient and pay a significant energy penalty for the capture process. As an example, a fossil fuel power plant with a carbon capture retrofitted would need to burn 20 to 30% more fuel to achieve the same output onto the grid. There is progress being made here in these projects, which include both direct source capture and scrubbing CO2 from the atmosphere. Achieving a true circular economy with carbon is the holy grail for this technology. Let's hope they achieve it sooner rather than later. Okay, enjoy the rest of your day, and I will see you at the next one.